Okay, let's delve into chapter 2. We're going to get a little bit more specifics about some of the terms that we need to know. We're going to talk about atoms, molecules, and ions. So let's go. Okay, so let's talk about matter. All right, we know matters everything, and if we look around at the variety, diamonds are transparent, salt is brittle, some things explode, gasoline can become flammable. These are macroscopic observations, things that we can see, but we don't necessarily know what's going on at the microscopic level. So we're going to start by looking at that macroscopic level and talk about I guess throughout the semester we'll go back and forth. We're going to sort of talk about what's happening at the microscopic level and relate it to the macroscopic. That's a lot of what we're going to be talking about this semester. All right, so let's say I tear a piece of aluminum. Let's draw a picture. I take a piece of aluminum foil and I cut it in half. Is that the smallest piece of aluminum possible? Get rid of that one. Obviously, no. What if I just keep cutting and cutting and cutting and cutting and cutting and cutting? Do I ever get to the smallest piece? Well, the answer is yes. There is something that once I get to that point, now obviously not physically, I can't really do it, but once I get to that smallest piece, if I cut it, I don't have aluminum anymore. So the atom is the smallest particle of an element that still retains the properties and characteristics of that element. So atom. Atomos is derived from the Greek word indivisible. So it's when it was first proposed, we didn't think it could be divided into anything smaller. We thought, oh, that's the smallest that we can get. Of course, we know now that we can divide it, but it won't anymore be. It won't look anything like what it is. So if I took an atom of aluminum and split it in half, I wouldn't have aluminum anymore. All right, so it turns out that some of the Greek philosophers, especially Democritus, was actually the first to argue that there is this limit to divisibility, that there is something that is the smallest that you can get to. Most people thought he was crazy, and they kind of dismissed him. So we went through the Dark Ages and all of that, and nobody ever thought about it again. And it was John Dalton, who you can see right here, this figure. He was really the first modern scientist to propose the atomic theory. In other words, that there was a smallest particle that represented that element. And so his theory became one of the essentials in modern chemistry. So let's look at his theory. Okay, he first said all matter is composed of indivisible particles that he called atoms. All atoms of a given element are identical to each other. Atoms of different elements are different from each other and have different properties from each other. Number 4, compounds are formed when atoms of more than one element combine. And we'll just look at a definition. So a compound is a type of matter composed of atoms of 2 or more elements chemically combined in fixed proportions. That's important. We'll talk about that in a minute. And then number 5, atoms of an element are not changed into different types of atoms, but they are only rearranged. So it's kind of the basis of chemistry back then in the early 1800s. We know that some of these theories, some of his postulates are not true, not totally true anymore. We've modified it, but again, this is sort of the basis for modern chemistry. So according to what he said, then a chemical reaction is a rearrangement of atoms present in the reacting substance to give new chemical combinations. It's not like one thing is changing to another, it's just a rearrangement of all the atoms, different combinations. And so we can say that atoms are neither created, destroyed, or broken into smaller particles by any chemical reaction. They're just rearranging it. So starting with Dalton, he is the first one. This gives us this picture down here, gives us what he thought an atom was, the smallest particle that if you can't divide it anymore. So that's Dalton's structure of the atom. Um, so here's just a few things to look at. So, here's copper. So pre-1982 copper penny had mostly copper. I think they're mostly zinc now, but anyway, there's copper atoms in there. They're sort of here. You can see in the picture they're kind of stacked one against the other. So each atom is identical to the other. Here, they're showing you a compound. Copper oxide is a powdery black compound, and it's a combination of copper, the brown ones, and oxygen, the red ones. In this case, copper 2 oxide, and we'll talk more about this in the coming chapters, it's a 1-to-1 ratio. CuO, we would write that as Cu. I'm trying to use my mouse as a writer. So anyway, CuO is the formula for this, which again we'll talk about later. But this is a compound, so it's a combination of 2 elements. It can be 2 or more. It doesn't have to be just 2. But the important thing about compounds is this: the law of definite proportions, or another way to say it is the law of constant composition. All samples of a pure compound will contain the same elements in the same proportions by mass. Right, so here we have an element, it's all the same atom. Here we have a compound which is made up of copper and oxygen. And again, no matter where you get copper 2 oxide from, it's always going to be in a 1-to-1 ratio in this case. Other compounds, like if you talk about CO2, CO2 is carbon dioxide. It always has a 1-to-2 ratio of carbon to oxygen, or H2O has a 2-to-1 ratio of hydrogen to oxygen. So a compound follows the law of definite proportions. All right, so let's talk for a little while about the structure of the atom. You probably already know this because you've taken science classes before when you've probably heard of protons, neutrons, and electrons. So let's talk about that a little bit. We know that Dalton wasn't exactly right. We can actually take an atom and break it into smaller particles. So experiments show that atoms consist of particles, but they happen to be, we'll talk about this in a minute, they happen to be the same particle in all atoms. So it's how many and how they're organized that are different. And so all these experiments that we'll talk about in just 1 minute show that the atom consists of 2 parts. There's a nucleus, which is the center, the atom's central core. It's positively charged and contains most of the atom's mass. And then there are at least 1 or more, well, doesn't have to be actually, there are 1 or more electrons in a neutral atom. There's at least 1 electron that are negatively charged. So there's electrons that are negatively charged, and they are light, much lighter than the protons, which we'll talk about, neutrons, and they exist in a region outside the nucleus. So let's talk about that. All right, so how do, just a little history of how the atom, the shape of the atom was discovered, the way the atom is organized. So one of the very first scientists back in the 1800s, J.J. Thomson, was actually the first one to discover or to determine that the atom was actually made up of smaller particles. So it was a long time. It was 1803 was Dalton, so it was nearly 100 years. Anyway, J.J. Thomson used what's called a cathode ray. A cathode ray is a stream of charged particles that go from the cathode, which is the negative end, to the anode, the positive end. And they had cathode rays, but they didn't know what was going on. And it's going to be in like a vacuum tube. So this is what a cathode ray looks like. In fact, the first televisions were based on the cathode ray. So if you put an electrical charge here, you've got this ray that's coming off of the metal. There's a metal over here. It's evacuated, so there's no air in here. And then the cathode ray, which is this green line, is shot out from the metal. Now, if you put charged plates, what happens is you see that the cathode ray is being drawn down toward the positive plate, which tells us that this ray is made up of negative charges. It's repelled from the negative plate and it's drawn to the positive plate. Here's an actual cathode ray set up. You know, and here there's no no magnet yet, but if we put the positive end of the negative down of the magnet down here, it will pull it down. Yeah, here you can see it. So you put the positive end and it pulls. This is actually a magnet, so it's not electrical, but same idea, magnetically attracted to the positive end, repelled from the negative end. I can't show in this video, I can't show you another video, but if you want to link on this YouTube video here, it's a real good one. It talks about the cathode ray. All right, so what did Thomson's experiment tell us? Well, first of all, it told us that atoms are divisible into smaller particles. He also determined that one of these subatomic particles was a charged particle, and in fact was negatively charged. It didn't matter which metal he used when he set up the cathode ray, and so it kind of indicated that all elements had the same negative particle in it. And so it's a common structure, subatomic particle that's ubiquitous, is everywhere. And so he called the negative particles electrons, and they are negatively charged subatomic particles. And it turns out they have a very, very small mass, much smaller than the atom. So that's what Thomson determined. Also, since there was some kind of negative charge there, and the overall atom was neutral, that means that somewhere in that atom there also must be some kind of positive charge. So he didn't know how they were arranged, and so this picture over here is sort of an idea that he had of what the atom looked like, a bunch of positive and negative charges just all mixed together. And sometimes it's called the plum pudding model of the atom because it looks like British plum pudding with little raisins all in there. Thomson was not able to calculate the actual mass of the electron or the actual charge of the electron. I know -1 would be the relative charge, but there's an actual charge we'll talk about in just a second. But he was able to figure out what the charge to mass ratio was. So the next scientist who was working around this time, Robert Millikan, performed his oil drop experiment. So I'll talk about it more probably on the next slide. He dropped an oil through a hole of an instrument, and he was actually able to, by changing the charges on the plates, he was actually able to stop a charged oil drop in mid-space. And by doing that and changing the voltage, he was able to figure out what the actual charge of an electron was. And you can see here it's 1.602 times 10 to the minus 19 coulombs. So it's kind of a meaningless number, but it was meaningful at the time. 1.602 times 10 to the minus 19 coulombs. It's an energy charge, a charge unit. And then because Thomson already knew the mass to charge ratio, then Millikan was able to figure out the mass of the electron. So you can see here 9.109 times 10 to the minus 31 kilograms, or if we change that to grams, it would be 9.109 times 10 to the minus 28 grams. So here's just a picture of the Millikan's oil drop experiment. He had these little oil droplets. He charged them, and so there were charges on these little oil drops. And then he was able to adjust the plates here. So he ionized these, and he made them negative, which means that electrons were associated with them. He was able to adjust the voltage here to just stop the dot in the drop in mid-fall, and then he was able to figure out what charge made it stop, and found, there's more to it, but found that the multiple, he figured out what the charge of one electron was. You can look in here and see what's happening. Again, this little video link will take you. It does a little video of the milk and oil drop. So if you want to watch that, you can. The next scientist around the same time was actually a student of Thomson's, and so he kind of took the work over from J.J. Thomson, and he was designing an experiment to find out more about the structure of the atom. So he designed an experiment where he shot alpha particles. Now, an alpha particle is a small particle. It's actually got 2 protons. An alpha particle has 2 protons and 2 neutrons. I know we're kind of mixing everything up because we haven't really talked about neutrons yet. But anyway, he didn't know what an alpha particle was at the time, but he knew that they were charged particles. So it's actually a particle that's got 2 protons and 2 neutrons, and it doesn't have any electrons. So it's actually a positive 2 charge. That's not an O. That's like a particle. It has a positive 2 charge. So they're tiny little particles that have a positive charge on them. And what he did, I'll show you on the next slide. So he shot them from this is they're radioactive, so that's why it's in the lead block. So he shot these alpha particles through a lead plate, and then they kind of got accelerated. And then this is a piece of metal gold foil, which is very, 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 very thin foil. And what he did was to figure out where along here these alpha particles would end up. So they kind of come through, and some of them hit here, some of them hit here. You can see the pink. Some of them got reflected backwards, or sort of, some of them, might go this way. They kind of had a full range. Some of them came way back and got detected over here. Again, here's a YouTube video about the gold foil experiment, which I think is a good one. But let me show you what this result told us. Okay, so Rutherford was able to revise the model of the atom from what J.J. Thomson, that plum pudding, and here's what he discovered, and we'll look at the picture in just one second. It'll make more sense. So most particles went straight through. What that indicated was that most of the atoms has empty space. Some of the particles, as I said, were deflected. This means they came close to something. If you came close to something that they had to rebound from, so they got bent away from it. And a few particles came all the way straight back, indicate they hit something solid. So let's look at the picture. I think it'll make more sense. Yeah. So you can see here, most of the particles came straight through. That means mostly it's empty space. This is exaggerated. These electrons are much bigger than they actually are in this picture. They should actually be much, much smaller. They're not the same size as the proton. We also found that a few of them got deflected, so they're scattered. So you can imagine if this was an empty black box, you didn't know what was going on, and then you threw a ball in there, and if it came out that way, you knew it had to have hit something. Right, so it was deflected. Or if it came straight back at you, you knew it hit something. So that's kind of the idea of it. He shot things into this empty black box and tried to figure out what was in there by how they reacted. All right, so again, most particles pass straight through, telling us most of this is empty space. Some of them were scattered. That tells us that there was something that the alpha particles encountered that made them kind of get deflected or move the other way. So what that sort of tells us is that this nucleus is positive because these alpha particles are also positive. So they were repelled by the positive nucleus. And the fact that some of them came straight through back the other way tells us that this is a very solid kind of got a lot of packed into that, so a very solid middle. All right, so this is kind of the structure that Rutherford came up, a model of the atom. This little link here, this PFET Colorado, if you want to try that out, it's actually a simulation where you can start throwing things at an empty box and see what the difference would be from Rutherford's model to Thomson's model. It's just like a little simulation. So I'll let you play around with that. Anyway, Rutherford's structure determined that most of the atom is empty space, like we knew, that the diameter of the atom is 100,000 times larger than the diameter of the nucleus. So obviously this is not to scale. And so this very dense positive charge in the middle. And we at this point still have no understanding of how electrons are organized in this outer space. And actually we'll save that for another chapter. I think chapter 5 or 6. We'll see when we get there. Anyway, we'll kind of leave it at that. All right, so yep, even though the modern picture of the atom continues to become more detailed, we're going to take this sort of more simple view. We know that protons can be subdivided into quarks and sparks, and I don't know all that. That sounds more like physics to me. So as chemists, we're just going to stick with protons, neutrons, and electrons. So anyway, at the time of Rutherford, he didn't know about anything about the neutrons, but he knew that there was a positively charged nucleus. So the nucleus of the atom is composed of protons and neutrons. The neutrons weren't discovered for about 20, 30 more years after Rutherford, but it turns out that those neutrons are in the nucleus, protons and neutrons. And the nucleus is a positive electric charge because those protons are positive. So the number of protons let's see, let's just go with what it says here. A proton is the nuclear particle having a positive charge. In a neutral atom, the protons are equal to the number of electrons. We'll talk about what happens if electrons are lost or gained in a minute, but for right now we're talking about neutral atoms, so protons will equal electrons because you have to have a neutral atom, so the charged particles have to be equal. A proton is more than 1,800 times the size of an electron. We know that the number of protons will vary, and that is what determines what the element is. So the number of protons in the nucleus is called the atomic number. The atomic number is given the symbol Z. I don't know why it's not given the symbol A. That would make more sense, but anyway, it's the symbol Z. So atomic number Z means how many protons there are, and that is, there's no veering away from that. If an atom has 6 protons, it's carbon. If it's carbon, it has 6 protons, and that's just the way it is. So the atomic number is the number of protons. An element then is a substance where all the atoms of that substance have the same atomic number. So like I said, if I've got carbon, that means there's 6 protons. And conversely, if I have 6 protons, that means I have carbon. There's no getting around. If I'm oxygen, I have 8 protons. And if I have 8 protons, there we go. If I have 8 protons, it's oxygen. So that is defined the element. Now, neutrons are neutral, thus the name neutron, neutral particles. The mass of a neutron is just about the same as a proton. They're about the same size, same mass, but neutrons are neutral, so they have no electrical charge. So they add to the mass of the atom, but they don't add to the charge of the atom. So here's just a summary of what we know about the atom. So the electron, and these are all in grams. So an electron, you can see here 9.1 times 10 to the minus 29 grams. A proton weighs quite a bit more than that. You can see almost a degree of almost, well, almost 10,000, no, is that right? 10,000 times bigger. Anyway, a proton's about 1.67 times 10 to the minus 24 grams. A neutron, almost exactly, maybe just slightly a hair more, but we're talking really tiny numbers, so mass in grams. The charge, we already knew from Thomson and Millikan that the charge of an electron is 1.602 times 10 to the minus 19. It's a negative charge. That's in coulombs. And so the proton actually has a charge exactly opposite of that, positive 1.602 times 10 to the minus 19 coulombs. A neutron, as we see, is neutral, 0 charge. Now, these are the absolute numbers, so the absolute mass, the absolute charge. I don't care if you remember these numbers or not. You want to remember the proton and electron are equal to each other but opposite sign. You want to remember protons and neutrons are about the same size, but very much bigger than electrons. But here, these are the ones that are relative, so relative to each other. So you can see here again, protons and neutrons are about the same mass. We're going to use a new unit called the atomic mass unit, AMU. AMU equals approximately 1.66 times 10 to the minus 24 grams. So that's kind of meaningless too. But anyway, relative to each other, we can see that protons and neutrons are about the same size. Electrons are way, way smaller. In fact, now we know they're not 0, but they really don't contribute any mass to the atom. So we assume all the mass is in the protons and neutrons in the nucleus. Right, nucleus. Okay, so we can almost think the mass of an electron is 0, mass of a proton 1, mass of a neutron is 1. We don't need to worry about these decimal places. And of course, the relative charge, we know that an electron is a negative 1, proton is a positive 1, and the neutron is 0. So these are important. These last two columns are the important ones for you to remember. Atomic mass unit, again, is kind of a made-up unit that's equal to this, but really all you need to do is remember AMU for now.